All right, welcome everyone. Welcome back. Thrilled to see you. Just making sure we can all hear and see all right. Feel free to hop in the comments, hop in the chat if there are any issues or questions regarding that. Otherwise, Daniella, all good on audio?
We're all good.
All right, fantastic. Well, we are so excited and so thrilled to welcome you back for those of you who joined us last time. And for those of you who are new, welcome to TestMax, welcome to GREMax. Just briefly, by way of introduction, I am Jonathan Herzog. I am the head of GRE content here at TestMax, completed my law degree at Harvard, went to business school at NYU Stern and undergrad at Harvard as well, and have helped tutor and instruct and teach classes in the GRE for 5 years now, helping folks achieve their dream scores and get into top schools across the country. And I'm thrilled to be joined by my awesome colleague here, Daniella.
Hi, everyone. I'm Daniella. I did my undergrad in business and engineering at Berkeley. Then I did my master's in public policy at Cambridge. I'm really passionate about the GRE, and it's really unlocked a lot of opportunities for me after trying to topple and after I struggled with the LSAT for a really long time. And the LSAT wasn't a fit for me, but the GRE was. And I'm really excited to take that energy as a GRE tutor, helping a lot of people get their, as Jonathan said, their dream scores and get into their dream schools. And I was also recently accepted to a PhD, actually multiple PhD programs in political science. So that's awesome. And I'm hopefully going to help you all as well.
Fantastic. Well, congratulations to Daniella. We're also happy for you. And to those of you on the call, feel free to shout out questions, comments in the chat, in the Q&A, and we'll try to flag them as we go. We're here to support you and help you unlock your dreams and potential when it comes to grad school. With that said, let us dive right in. So today we're focused on the quantitative reasoning portion of the GRE, of the graduate records exam. Now, if you're interested in a broader overview about what the exam is and how it's used in application to grad school, be sure to check out on YouTube, the TestMax channel, our webinar from last time, which will give you that broader foundational overview of the test itself. But today we're focused on the quantitative reasoning portion. Now, just a couple of big picture messages here. What is the quantitative reasoning portion? First and foremost, it is not a math test. It's a common myth in the GRE parlance, in GRE land. What it is a reasoning test that uses the language, logic, and syntax of math. And we'll dive into some of the foundational rules in a particular sector today and apply this to some real practice questions, and we'll see what this looks like in action. So a couple of the common refrains we'll hear from students that we worked with over the years include, I'm just overthinking, or I'm just running out of time on quant, I'm just not a math person, or I'm just not a geometry person. And in fact, I've heard some of these phrases come out of my own mouth as well. Because one of the philosophies of TestMax and GREMax in our hiring is we only hire folks who, A, have excelled and achieved top scores on the GRE, but weren't naturals coming into it. So we've had to reverse engineer the test and break it down to first principles, as we had to do when we were navigating and struggling through the test ourselves. But so what all these common sayings actually mean is they're euphemisms for I haven't yet mastered the quantitative reasoning skills sufficient for my target score. And we'll see a number of examples through this conversation tonight, but we really try to lean into a behavioral and cognitive science approach to our teaching and instruction that can unlock the biggest impact with the most efficient use of your resources and time. All right, so what is the quant section? Again, what is it comprised of? The substantive skill areas are of high school mathematic levels. And so those include arithmetic, algebra, geometry, and data analysis. These are the 4 big buckets of the types of tools and skill set that we'll have to remind ourselves of and retrain bottom up in order to apply to the reasoning tests that we'll see. Just a few brief reminders as well. Your quant score is one of those two big 130 to 170 scores on the GRE. So that's the scaled score you'll see immediately after you take the test on test day, where the top score of 170 gives you that 96th percentile on the quant section. So that's one of the two big numbers you'll get right after on test day. And if we hone in just on the quant section here to remind ourselves what we're even looking at, what the big picture is, we're dealing with two sections and possibly an experimental or research that are specifically quant. Each is going to be 35 minutes with 20 questions each. So that's it. That's all that makes up that 170, that magic score on the quant section of the GRE. So with this, we're going to pivot ever so slightly into the quant section itself. This is a breakdown of what the questions look like in terms of the types of quantitative problem solving you're going to be doing. So about 7 to 8 are going to be quantitative comparison, which is going to be the type of questions we'll dive into in greater depth today. 3 to 4 are going to be quant problem solving, followed by another 5 to 6 of quant problem solving, scattered in the middle and the end. And you'll have 3 to 4 of stricter data analysis, looking at some charts and graphs and interpreting the numbers that are associated with them. So today we have the great fun, the great thrill of diving into exponents, which is going to be a subset of that bigger bucket of algebra. So this is just one of the subsections of one of the 4 big sections that we're going to master to get our target score on quant. Now, I want to start off with a bit of a preface on why the heck, if you plan to be applying to grad school, whatever it might be, any master's, PhD, MBA, JD program, you name it, why are we restudying the rules of exponents? And I found that working with students, and even for myself, really understanding the why behind what we're doing can help unlock our performance on the quant section. So exponential thinking has really powerful ramifications both in our personal, professional lives. And this is just one example from a recent popular book on forming habits and habit formation in our own lives. As you can see here in the chart, if you have 1% worse every day for 1 year, so that's 0.99 to 365th power, that's going to get you 0.03. If you get 1% better every day for 1 year, say whatever habit that might be, that's going to be 1.01 to the 365th power, and that's going to be nearly 37 times better after 1 year. So we'll look at a couple of other examples, but the power of exponential thinking and exponential growth is really hard to overstate. Now, we're all unfortunately familiar with this in this really difficult time with the COVID pandemic. And one of the many analyses looking at the public policy response and really the evolution and the replication of the virus related to our human cognitive bias for linear thinking. And so this is just a quick example looking at the charts for what linear versus exponential growth can look like in replication of this viral pandemic. So on day 2, the linear would equal the exponential result. You would have 3. On day 3, the exponential would grow a little bit faster, so it would be 9 as opposed to 6. On day 4, 27 exponential, 9 on the linear. But by day 7, 1 week into the pandemic, if we think back to March of last year when the first noted case happened in the United States, 1 week later, with exponential growth, 729 cases versus 18 in the linear case. And this just illustrates the importance of training and thinking and having mental dexterity in the tools of exponents. So when we get into the numbers and the practice questions in a moment, this is sort of the big picture of why this type of thinking matters in the real world, in the real practice that we'll all go on to do after pursuing graduate school. So these are a couple of headlines. Again, our brains are literally wired for linear thinking, the value of exponential thinking, and the exponential growth bias, the numerical error behind COVID-19 and many of the public policy approaches. And finally, to close out our sort of brief introduction to why exponents are awesome, we have the one and only Albert Einstein, who said, "Compound interest is the eighth wonder of the world. He who understands it earns it. He or she who doesn't pays it." So with that, again, feel free to hop into the chats, into the questions as we go, but we're going to dive right in. So quantitative comparison. Just as a brief reminder for those of you who haven't seen this question type before, questions of this type will ask you to compare two quantities, quantity A and quantity B, and then determine which of the following statements describes the comparison accurately. Choice A, quantity A is greater. Choice B, quantity B is greater. Choice C, the two quantities are equal. Choice D, the relationship cannot be determined from the information given. All right, so the answers on quant comparison are going to be our friends, and we're never going to read them again. A is always going to be A is bigger. B is always going to be B is bigger. C is going to be they equal each other. And D is going to be, I don't know. All right, the moment you've all been waiting for, the 25 basic rules of exponents. So we're going to overview the 25 basic rules that then we're going to apply in action to real, live, actual GRE quant comparison questions, specifically in the exponents domain, again, that subsection of algebra. Alrighty, so to get us started, make sure we're using the same language, the same vocabulary here. We'll pull out our handy dandy pencil or our iPad, and let's get going. Exponents is just multiplication on repeat. Some terms we'll hear, and we can recall from grade school, are the base, which is the number being multiplied, and then the power, or the exponent, which is the amount of times the number will be multiplied. So in this particular example, let's take the base 2, the number 2, and we're going to raise it to the power of 6, or raise it to the 6th power. As we recall, all that simply means, all the instructions we're giving is, hey, take 2, multiply it by itself 6 times. 2 times 2 times 2 times 2 times 2 times 2, and that gives us 64. Fantastic. A couple of other common terms we'll see and use in our conversation include square, which just means to the power of or to the exponent 2. So if I take base 2 to the power of 2, or 2 squared, that, as we know, is going to be 2 times 2, which will give us 4. And likewise, cubed is just the exponent of 3, so you multiply it by itself 3 times. 2 times 2 times 2 gives you 8. Again, we're going to start really basic, really foundational building blocks to make sure there is no confusion as we go, because it's going to ramp up exponentially. All right, we're going to clear our screen and move down to the first 5 rules. So rule number 1, take a variable to a power. It turns out it's the same thing as what we just saw in taking a number to a power, right? So the variable is just standing in for some number. In this example, x cubed simply means, hey, take x, multiply it by itself 3 times. Fantastic if you want to check our work. One of the tools is substituting a value, testing simple numbers. So again, let's pick 2 because it's pretty easy. 2 cubed, 2 times 2 times 2. All right, we're getting the hang of it. 0 to a power. 0 to a power is always 0. That's pretty much it. Now, we will see this caveat here and there, which is that for a power greater than 0, all this is this subset of the math world, which is dividing by 0 is undefined, if we recall that from our grade school years. But the good thing for the GRE is we really don't have to worry about it. In fact, oftentimes in the quant comparison section, the test makers will simply tell you it just can't be 0. So again, 0 times itself is going to be 0. All right, 1 to a power is always 1. We have the example 1 to the 4th, 1 times 1 times 1 times 1, and it still, in fact, is 1. All right, so we're dealing with zeros and ones and variables, right? Or just some kind of substitute for a particular number. Well, what is this? It's a little bit stranger. So if we're given x is equal to x squared, or if we solve an algebraic equation and find that x is equal to x squared, then it turns out that x can only be one of two things. X can either be 0 or 1. Now, how do we really know that? Well, we can prove it to ourselves. So again, in our simplifying algebraic equations, a whole other skill set, a whole other chapter and part of the algebra section, we're going to subtract x from both sides of the equation. And we're going to get x squared minus x equals 0. We're starting to integrate some of our algebraic toolkit already, and we're going to see this in a moment, but we're going to factor out the lowest common power term. So in this case, that's going to be x to the 1. However, more often than not, that 1 will be hidden. So when we just see an x or a variable on its own, there's an implicit or a hidden 1 there, right? Because it just means, hey, take x, multiply it by itself once. So we just have x. Great. So we pull out, we factor out that x, and we get that x to the 1. Again, the 1s are all hidden. And it turns out we actually get x to the 0, which, as we know, we're already integrating like 3 or 4 exponent rules in 1 is equal to 1. So we have x times x minus 1 is equal to 0. And again, from our algebraic toolkit, we know that either x is going to equal 0 or x minus 1 will equal 0. In that case, x will equal 1. So that is why, if we're given x is equal to x squared, or if we solve for it, giving a more complicated algebraic equation, we know x has only the possibility of equaling 0 or 1. All right, now we're getting into some negatives. So we're going to deal with a positive and negative signs. And again, we're just walking through the basic 25 rules of exponents, because then we're going to see immediately how they unlock immense power on actual GRE questions. All right, so rule 5, -1 to an odd power. -1, in the example here, to the 5th power. So it turns out when we raise it to an odd power, it's going to keep the same sign of the base. In this case, the base is -1, so it's just going to keep that sign. One other way of thinking about it, which we'll see in a moment, is what happens when you have pairs or an even power of negatives. In fact, in that case, moving on to rule 6, -1 to an even power will be 1. So take the example of -1 to the 4th. That's -1 times -1 times -1 times -1. Each of these pairs of negatives is going to, quote, cancel each other out and going to turn into a positive. So this again brings us -1 to an even power. Whether that even power is 2, 6, 8, 32, 128 is still going to be 1. All right. So let's draw up here a little number line, because we're going to get, so we dealt with zeros, ones, variables, and the intersection of those three. Now we're looking to what happens between the zeros and the ones. So on our standard number line, we know we have our neutral 0, and we have values greater than and less than 0. The values that are greater than, we call positive. The values that are less than, we call negative. Fantastic. So now we're looking at what happens in this liminal space between 0 and 1. So it turns out a fraction between 0 and 1 to a power gets smaller. In other words, it approaches 0. It approaches the neutral center of the number line. Again, we can prove this to ourselves by picking easy numbers. In this case, let's look at the example of 1/2. 1/2 squared, hey, take the base, multiply it by itself twice, okay? 1/2 times 1/2 gives us 1/4. You can convert this to decimals to also have another intuition for which is greater and which is less. When you take it to the third power, you multiply it by another 1/2, and that gets you 1/8 or 0.125. So notice it's getting smaller and smaller and smaller, and in fact, it's approaching 0. And so this is the key condition when our fraction is between 0 and 1 raised to a power. All right, let's erase some of this. What if we have that negative side of the number line and we have a fraction between -1 and 0, right? So to the left side of 0. A negative number, a negative fraction raised to an even power is going to get larger. It's still approaching 0. So we're seeing a trend here, right? Fractions, when raised to a power, seem to be approaching 0, but negatives introduce another complication. In this case, if it is raised to an even power, that is a negative fraction between -1 and 0 raised to an even power, it approaches 0 and gets larger, but that's because it gets positive. So let's look at -1/2 squared. -1/2 times a -1/2. Again, that pairing of negatives, that two negatives gets you a positive, and we know that gives you 1/4. So indeed, 1/4 is bigger than -1/2, but if we recall on our number line, in part what happened is we jumped over the 0. So still it's approaching 0, it's going to be positive, and it is indeed getting larger. All right, let's look at the other case. We're getting somewhere. Rule number 9. We have a fraction between -1 and 0, but this time it's taken to an odd power. All right, so recall already, we're pulling together, looping in some of our other rules of exponents. So this time we're raising it to an odd power, which we know is going to keep the sign of the base. We saw that before with the 1 and the -1. We're still dealing with a fraction that is negative between -1 and 0. It still gets larger. It still approaches 0 because that's what fractions raised to a power do if they're less than 1 or greater than -1. But this time it's just becoming less negative. So it's staying on the same side of the 0. Again, we look at a simple example. -1/2 cubed, -1/2 times -1/2 times -1/2. That double negative becomes positive, but a positive times a negative, which again is a whole other section of dealing with positives and negatives and the signs of numbers. It's a whole other section that we're going to train on. That gives us -1/8, which is closer to 0, but still negative. So again, the distinction there on negative fractions between -1 and 0 raised to an even versus odd power, both approaching 0, but for different reasons. All right. Now we're going to take a look at rule number 10. Same base multiplication, add the exponents. Again, we've probably seen many of these rules or can intuit them from much of our grade school or high school work, but we're just going to lay them out because we're going to apply them in succession. So a to the n times a to the m is going to equal a to the n plus m. Okay, what does that even mean? Let's pick some easy numbers. So let's say a is equal to 2. So let's say we have 2 squared times 2 cubed. Is it in fact the case that that is equal to 2 to the 5th or 2 to the 2 plus 3? Right, because that's what the rule is telling us. If we have the same base and we're multiplying that base raised to an exponent, all we got to do is add the exponents. So again, we started out with differentiating the base and the exponent or power, and now we're multiplying two values that have the same base, but now we're adding the exponents because they're being multiplied. So we can actually do the math ourselves. 2 squared is 4, 2 cubed is 8, we know that from before. 32, that is indeed what 2 to the 5th is equal to. And we can test this out. either by memorizing it or knowing it or reverse engineering it or plugging it into our calculator. Many, many ways to end up seeing the same exact thing, which proves the rule that a to the n times a to the m is equal to a to the n plus m, or supports it. All right. Rule number 11, same exponent multiplication. In this case, we're going to multiply the bases. So we have a to the n times b to the n. So the exponent is identical. In this case, we can multiply the bases. So we can reverse engineer this as well. But if we want to stick to the simple, easy case, let's say we have 2 squared times 3 squared. Is that in fact the same as 2 times 3 squared? Exponent's the same. They're telling us, or we're telling us, to multiply the bases. Is that the same as 6 squared or 36? Well, let's check. 2 squared is 4, 3 squared is 9, 4 times 9 is in fact 36. So we can reverse engineer this backwards. We can do that at a later time, but the rule still stands. Rule number 11, a to the n times b to the n is equal to, in parentheses, a times b, all raised to the power of n. All right. Almost there. Rule number 12, same base division, subtract the exponents. Okay, so we're going to pick different variables because variables are just standing in for any number, so we can use any letter we want. Let's say x to the n over x to the m, that is equal to x to the n minus m. So recall, we saw if we had the same base multiplication, we were adding the exponents. In this case, we're dividing, and we're going to have to subtract the exponents. Let's test a simple case. 2 squared over 2 cubed. The rule tells us we have the same base, so we can do 2 to the 2 minus 3. 2 minus 3 is -1. 2 to the -1. We'll get to those in a moment. But that is 1 over 2 to the 1, or 1/2. Let's check it. 2 squared is 4. 2 cubed is 8. 4 over 8 simplifies down if we divide both the numerator and denominator by 4. Indeed, it gives us 1/2. So the rule checks out. Similar principle as before, so we don't have to test this one. Same exponent division, just like we could distribute out the exponent before. Same thing here. X to the n over y to the n is the same thing as x over y, all raised to the power of n. All right, so we just saw an example of this when we took 2 to the -1. But when we see a negative exponent, what this is telling us to do, the instruction, the rule it's telling us, is, hey, take 1 over the base to the positive power. Again, we have that finicky little caveat of x not being 0 because we can't divide by 0. We don't have to worry about that. But just for completeness sake, it's good to mention. So x to the -n is equal to 1 over x to the positive power, right? So x to the n is not just the positive version of x to the -n. We just saw this example with 2 to the -1, which is going to be 1 over 2 to the 1, or 1/2. Same principle applies because we know what we can do to numbers, we can also do to variables. So we can take that with the y over 5 or other examples. Let's take a look at rule 15. All right, this is a little bit strange. X to the power of 0, as we may recall, is equal to 1. Again, the same caveat, x not itself being 0. So x to the 0 is equal to 1, is equal to 1. So that means 5 to the 0. That means 256 to the 0th power. All of those equal 1. Well, how come? Let's take a look. So it's the same principle actually that applies in the division and subtraction of exponents we actually saw in a previous rule. So feel free to revisit and go back to the previous rules to gut check and make sure all the rules really fit into one another. In this example, we have x to the 4th over x to the fourth. So what that rule tells us, we're just multiplying x by itself 4 times, x times x times x times x over itself. All right, well, each of those in turn is going to cancel each other out and give us 1. Alternatively, from the previous rule we saw, we know we can just subtract the exponents. So x, right, to the n minus m, or whatever the exponents are. In this case, it's 4 minus 4, which gives us 0, which gives us 1. So we can reverse engineer the rule or just recall it so that we don't have to derive it every single time we use it or see it on the GRE. All right, rule number 16. And we're seeing some trends here come up over and over and over again, and the GRE loves them. Those trends include fractions. Those trends include the zeros and ones and the positives and negatives, the signs of the numbers, and those causing very different results when we're actually solving problems. In this case, negative x to the y is not necessarily the same as parentheses negative x to the y power. So let's take a look at an example here. Let's say x is 2 and y is 3. Again, just picking easy numbers here. So in the first instance, we see negative 2 cubed. In the second instance, oops, sorry, let's pick a different, actually this is instructive. All right, so let's look at the contrast here. If we had x equals 2 and y equals 3. In this case, we're going to, with Pemdas in the order of operations, parentheses, exponents, multiplication, division, addition, subtraction, which again, a skill we're going to build in a whole other section in our arithmetic section. This is going to come out to 2 cubed, so we're going to do the exponents first, 8, and then apply the negative to it. In this case, we're going to take negative 2 times negative 2 times negative 2. So that pair of negatives is going to give us a positive. So that's going to give us 4 times negative 2. So it's going to give us the same thing in this case, negative 8. But what if y is equal to 2? So let's keep that in our minds or in our notes. But if we have the case of x equals 2, y equals 2, let's see what happens. We have negative 2 squared, and we have negative 2 squared. All right, so we have our training in Pemdas. We know the exponent is going to come first in this case. So 2 squared, 2 times 2 is 4. We apply the negative to the 4. It's like taking a negative 1, multiplying it by 4. In this case, we're taking negative 2 times negative 2. All right, so the 2 negatives cancel out to a positive, and whoa, this gives us 4. All right, so we're seeing that in the case of even exponents, again, the difference between the even versus the odd, that trend coming up again, it's important to look out for whether or not the base is in parentheses, particularly when it's negative, because as we see, when we take it to an even power, it's going to make it positive. All right, we're almost there. Rule number 17. Power of a power, we're going to multiply the exponents. So if we have x to the m to the n, or in this example, x cubed squared, which just tells us we're going to start with the outer exponent, right? Same basic principle that we had initially, like 2 squared, except here we have x cubed instead of 2. So it says multiply x cubed by itself twice, so x cubed times x cubed. And what we found from before is we can add the exponents. So that's the same as saying x to the 3 plus 3, or x to the 6. So it turns out we can simplify this. Again, we don't have to reverse engineer and prove it to ourselves every time, but just recall through practice, through drilling, that when we take a power to a power, we multiply the exponents. All right. So remember when I said, we're going through exponents, we're going through practice questions, and we're like, oh gosh, like really, we're going back to exponent rules? But recall that initial framing. What are the stakes, right? What are the stakes in whether we can grasp and hone and apply exponential thinking. In the case of, say, the United States, more than 500,000 COVID deaths. So this is just the context of what exponential growth can look like versus linear. All right, back to the rules. Rule 18, adding the same bases with the same exponents. So sometimes the bases are different, sometimes the exponents are different. We have different rules for each. But in this case, we have the same base and the same exponent. It turns out all we got to do is just multiply it by the number of times we had that same base with the same exponent. We can always derive this for ourselves. So we have 2 squared plus 2 squared. That's 4 plus 4, which is equal to 8, which indeed is equal to 2 times 2 squared. All right. It gets a little bit more complicated when we factor out terms that are being added or subtracted with the same base. So if we have 7 to the 4th plus 7 to the 5th, that is not automatically equal to 7 to the 9th. No, right? Because that's the case. We're going to add the exponents if we're multiplying. So not this time. Instead, what we can do is factor out the smallest power. So we did this before when we used the variable example. In this case, it's the same. We're just using real numbers. So we factor out the smallest power component of both 7 to the 4th and 7 to the 5th, which is 7 to the 4th. Because again, all this really means is 7 times itself 4 or 5 times. This is the 4th and this is the 5th. All right, so we factor out 7 to the 4th. We saw the same exact thing before with our variables. What do we get? Inside the parentheses, when we factor out 7 to the 4th from 7 to the 4th, we just get 1, or 7 to the 0 power. And when we factor out 7 to the 4th from 7 to the 5th, we just get 7 to the 1st power. Because this is what it means to factor out, is that 7 to the 4th times what would equal 7 to the 5th? Well, 7 to the 1st power, because we're just going to add the exponents. All right, so in this case, we like that this is in a product. It's being multiplied. So we have 7 to the 4th times 7 to the 0 plus 7 to the 1. We know, integrating and applying all of the rules from previously, that that is just going to simplify to 1 plus 7, or 8, times 7 to the 4th. Again, that instinctive response to see 7 to the 4th plus 7 to the 5th and just turn it into 7 to the 9th is not supported by the data if you actually ran the calculations by hand, nor is it supported by the rule in the abstract. All right, we're almost there. So, rule number 20. It's getting even more complicated. It's all building on itself. So sometimes, and we're going to be asking for finding, say, the greatest prime factor. Or in this particular case, we're applying the same mechanism of factoring out of this string of numbers, 7 to the 33rd plus 7 to the 34th plus 7 to the 35th, which seems really complicated on its face. But we're boiling it down to the same exact principle, the same exact process as before. So we're going to factor out 7 to the 33rd from each of the terms. So we ask ourselves, what multiplied by the smallest power, 7 to the 33rd, gives us each of those terms in turn? Well, first, 7 to the 0, or 1, because the first term is just 7 to the 33rd itself. Plus, the next term is just another 7, right? That's what that 34th means. It means that we're just multiplying 7 all the way 34 times by itself. And finally, we have 7 squared for 7 to the 35th power. Same process as before, as when we're factoring out, and we just have seemingly complex terms being added. This turns into 1 plus 7 plus 49. We have 7 to the 33rd times 57. We break that down, And this is a whole other lesson on prime factorization and finding the roots and factors, which is a whole other fun lesson, but not for today. 7 to the 33rd power times 19 times 3. And it turns out that the greatest prime factor of this whole set is 19. So just another way of applying that factorization of when we're adding seemingly complex terms that get broken down using the same principle, the same rule as before. All right, rule number 21. We saw this before, which is negative exponents, we're taking the reciprocal or the flip to the positive power. But again, we can always take the abstraction. So in this case, if we have x over y, or substitute anything else you want over that, to a negative power, we're gonna flip the terms, flip the numerator and the denominator, and take it to that same power, but the positive version of it. All right, if you're still with us, we're in the final stretch of our rules before we dive into the questions. So, rule number 22, part A. And we've seen this before, again, expressed in different ways, but with even exponents, the result explicitly is always positive, regardless of the base. So we saw this in the trickiness of whether we have a negative base and we have a negative base in parentheses. But as a rule, with even exponents, the results are always positive. Without exponents, the results take the same sign as the base. So we saw, again, we're deriving this from a combination of a number of rules we saw before. We can prove this to ourselves by picking numbers. Rule number 23 is sort of a caveat, a qualifier on some of the others. Not all equations with exponents will have two solutions. Some of them, again, will boil down in some of these cases where they simply equal 0. All right, we're going to race through the last couple just in the interest of time to get to our questions. Number 24, we're actually going to apply today. In particular, if the bases are the same and there's a variable in the exponent, then the exponents can be equated to find their value. So look at this case. 6 to the 10x is equal to 6 to the 20th power. Because the bases are identical and there's a variable in the exponent, just the rule, written out, we can equate the exponents to solve for the variable in the exponent. Again, with our caveats, where 0 and 1 can be complicated, this does not hold if the base is 0 or 1, since, as we know, the outcomes there are unique. All right. We'll save the radicals and the absolute values for another time. But now, I'm absolutely thrilled to pass it on to Daniella to dive into our first GRE quant practice problem of the day.
Awesome, this is so exciting. So now we get to use the skills that we've learned and apply them to a couple of practice problems. And feel free, if you have any questions, please send them into the chat box and I'd be happy to answer them. So what we're going to do is I'm going to share my screen really quickly. And Jonathan, may I have...
I think you should be able to write on it.
I should be able to write on it. Awesome. Okay. So just let's try this out. Oh, awesome. Okay. So we're looking at this question, which is a quantitative comparison question. As Jonathan mentioned before, there's only 4 answer choices. A is greater, B is greater, the two quantities are equal, and the relationship cannot be determined from the information given. So what's my favorite rule with quantitative comparison questions? It's can D be an answer choice? And this way we're positioning ourselves at getting into the test maker's mind and trying to understand, can D be an answer choice? And what we're thinking about here with quantity A being K and quantity B being -2 is, can we solve for K? Do we know, is there a finite answer to what K can be? And the answer for us right now is yes. We do know what K can be, and we can solve it based on what the rules are that we learned today. So the rule that we just learned is that there's two bases that are the same, there's the exponents can be equal. So let's just look at this here. can we simplify? Can we change either of these bases to be 2? And in fact, yes, we can. So this equation can be rewritten as 1 over 2, 1 minus k is less than 1 over 2 to the third, because 2 times 2 times 2 is 8. So now we see the two bases are the same, and therefore we can equate the two exponents. But before that, there's this 1 here, and that's a problem. And to do that, what we can do is we can say 2 to the 1 minus k is greater than 2 to the third. And what we just did here is when we multiplied by -1, we had to switch the greater than symbol to the less than symbol. And so I'm just going to say 1 minus k over here is greater than 3, because we're just taking these whatever in the exponents, and then we will solve. So negative k is greater than 3 minus 1, which equals 2. Let me just clear this out so it's a little bit more clear. I'm actually going to go over here, everyone. So then we'll get to 1 minus k is greater than 3, and then we'll get negative k is greater than 2, and k is less than -2. Here, quantity b is -2, and k must be less than that. Therefore, quantity b must be greater. Let's clear that out and move on, if we don't have any questions, to the next question.
Fantastic. So one just quick reflection, because Daniella really integrated a number of complex rules, including from inequalities and flipping the sign of the inequality when we're using negative numbers. But an alternative way of presenting the same thing, as Daniella showed us, is to just take 2 to the negative of 1 minus k and just take that as 2 to the k minus 1. So whether you're automatically integrating how inequalities relate to negatives and flipping the sign, or just taking, if we see 1 over 2 to a power as 2 to the negative of that power, that enables us to get the same exact result. Lots of ways to get to Rome.
Many ways. Again, we'll go through this next problem, and if any of you have any questions, feel free to let us know again. Right now, for this question, we don't see a quantitative comparison, so that means the multiple choice question, which means that we can't eliminate any sort of answer choices up front right off the bat. This question is asking, what is the least integer n such that 1 over 2 to the n is less than 0.001 or 1/1000th? And we need to find what's the least integer n. So what I'm going to do, the first thing that comes to my mind is how to get a number by itself, how to get the n on one side of the equation and values on the other side of the equation. And I want to get the 2n, this funky thing, alone. So what I'm going to do is I'm going to think of the inequality as if it's an equal sign, which we can do to manipulate equations sometimes, always keeping that negative in mind where you have to flip the inequality sign. And simplify the equation so that it looks like 1 is greater than 0.001 times 2 to the n. And then we're going to divide as we're trying to get the 0.001. And we have 1,000 is less than 2 to the n. So now it's asking, so now that we have the n on one side and a value, a constant on the other, let's return to the question. What is the least integer n such that 2 to the n is greater than 1,000? And we have here the least integer. So let's try this out. Okay, so I'm just going to rewrite our equation up here. 1,000 is less than 2 to the n. And we're going to use our least integer and find out what that is. So I'm just going to erase, for the sake of time, some things here, as we're going to now look and see what are the values of 2 to the n. Okay. So let's just write them out loud together. So 2 to the 1 is 2. 2 to the 2 is 2 times 2, which is 4. 2 to the 3 is 4, which is 2 to the 2, times 2, which is 8. 2 to the 4th is 8 times 2, which is 16. 2 to the 5th, 2 base 2 to the 5th equals 16 times 2, which is 32. 2 to the 6th is 32 times 2, which is 64. 2 to the 7th is 64 times 2, which is 128. 28. 2 to the 8th is 128 times 2, which equals 256. 2 to the 9th is 512, which, oh, whoops, I got ahead of myself there, is 512, 2 to the 9th is 256 times 2, which is 512. And we can, and now 2 to the 10th, we can see that because we don't even have to do 512 times 2, because 512, we know, times 2 is going to be greater than 1,000, because 500 times 2 is 1,000. So we don't even need to do it, and we find out that the correct answer choice here is A. Jonathan, do you have anything else to add, or maybe another approach?
Yeah, this is what's so fantastic is there's so many different ways to solve the same problem. And Daniella walked us through what we can end up intuiting or memorizing, right? Which is the powers of 2 that we're going to see over and over and over again. But it's great to see them laid out because those common numbers are going to reappear over and over and over again. But again, there's lots of ways to tackle the same problems using those same basic 25 exponent rules and integrating some of the rules from other sections. So in this case, as Daniella said, we have 1/1000th, which we'll get used to converting to 10 to the negative power of. So it's 10 to the negative 3, which is equal to 1 over 10 cubed, because 10 squared is 100, 10 cubed is 10 squared times 10, which is 1,000. And in this case, again, we saw from before, we can just take 2 to the negative n as another way of reframing it. So lots of ways to solve the same problem. What we end up seeing is that integrating all of the rules from before, this is going to be 1 over 2 times 5 cubed, right? That's just 10 cubed. So 2 cubed times 5 cubed. And on this side, we're going to have just 2 to the n. All right, we're pulling together many of our rules. We know we can just distribute the 3 because the bases are being multiplied. So we're basically comparing 2 to the n and 2 cubes times 5 cubed. Now, this is one of the funny things about fractions, is that if we want the right-hand side, in this case, the 1/1000th, to be greater than the left-hand side, in this case, 2 to the negative n, or 1 over 2 to the n, we want the denominator on the left-hand side to be bigger, because that makes the number smaller. If it's divided by a bigger number, then that makes the overall number smaller. In this case, we can simplify 5 cubed, 5 squared is 25, 25 times 5 is 125. Again, we'll drill in these often repeating patterns of exponents. And we're really comparing then ultimately just 2 to the n and 125 times 2 to the third. And using the same exact principles and rules that Daniella applied, just using a different approach, a different process, we end up finding essentially the same thing, which is that we need 2 to the 7th times 2 cubed to get us at least to that power to be greater than 125 times 2 cubed. So same rules, slightly different process, and same outcome, which indeed gives us the least integer being 10. All right. We got another fun one here. Again, a multiple choice, again, using exponents. So 1 over 2 to the k plus 1 over 2 to the k is equal to 1 over 2 to the x. Then what is x expressed in terms of k? All right, well, so the wheels are spinning. 1 over 2 to the k, we already know this expression as the same as to the negative k, right? Because that's 1 over 2 to the k plus 2 to the negative k. Just rewriting it another way to see if we can see a hint of what rules we can use is equal to 2 to the negative x, right? So we've just rewritten the fractions in what seems to be a potentially easier fashion. Now we know we have the same bases, the same exponents. We can just take the number of times we have that times the same base and same exponent. So in this case, that is 2 times 2 to the negative k, because we got 2 of them, right? We saw that same exact rule before, is equal to 2 to the negative x. Now, we know that hidden 1, and we know what happens when we multiply with the same base, and so then we add the exponents. So in this case, it's negative k plus 1 is equal to negative x. Let's always recall what the question was, because we're certainly going to have trap answers that don't correctly solve the question. In this case, we're given negative x. Using our positive negative rules, we're going to divide both sides by negative 1. And we're going to flip the signs on the left side. And that's going to bring this k minus 1 is equal to x. And again, multiple ways to arrive at the same result. It just depends about which ends up being easier, simpler, more efficient, but also correct for you. All right. And rounding out our practice real GRE quantitative comparison questions here, we're back to our quantitative comparison. We know what our answers already are. A is bigger, B is bigger, they're the same. We can't determine from the information given. We have a constraint up front that tells us x is bigger than 1. All right, good to know. And then we have quantity A and quantity B. All right, we're seeing all of the same rules in action. So let's start with quantity B. So a power to a power. X cubed cubed, what do? We multiply the powers. X to the 3 times 3, which is equal to x to the 9. Now note, sometimes it may be easier to pick numbers. Sometimes it may be easier to simplify an expression, which is what we're doing here. Because you wouldn't want to, if you didn't recall off the top of your head what 2 to the 9th was, you don't want to go through and say, test a case. We can just keep it in the abstract in this case. X to the 9th. Back to the left side, back to quantity A, power to a power. We multiply the powers, x squared to the 4th. So that's x to the 8th. Times, again, we have that hidden 1. It comes up over and over again, x to the 1, right? Or just x. This time, we're going to add the exponents because we're multiplying the same base. So that's x to the 1 plus 8, which is equal to x to the 9th, which indeed is equal to x to the 9th in generality. Again, you could pick a test case and actually find that indeed this is the case, but you don't have to because the quantities are equal. All right. With that, again, please feel free at any point to shoot fire in any questions, thoughts, reflections about GREMax, TestMax, about any of the questions or content we're seeing here today. But we're going to round it out with a couple of brief high-level reflections on the GREMax difference. So as you may have got a taste for today in this specific quant section, our focus is on bottom-up, skills-based foundational training. We're not here to hack bad tests. We're here to teach for a good, which means a predictive test, right? We saw those same 25 basic exponent rules, then translated, combined into pretty annoying or complicated questions, but those are the same building blocks, the same foundational 25 rules that we're gonna see applied over and over and over again, just different wrapping paper. We don't believe you should put your life on hold for the GRE or for grad school admissions. This is all of ours, one precious life. And to that end, again, we've boiled it down really to the foundations, the principles that you can apply rigorously and apply to skill-based drills, and then extend them to actual practice official test prep questions. We don't use unpredictive, made-up questions. We only use official test prep questions, which is another part of the GREMax difference. And I want to briefly walk through just one example of this cognitive triad that we talked about on our last webinar, but how it applies particularly to the quantitative section of the GRE. So let's say we have a circumstance, a neutral fact in the world. Say you did a practice test, or you've taken the GRE before, or you studied for 3 years, or you just did one quant question, whatever it might be, fine. Let's say the circumstance is I got 10 quant questions wrong. That's just the neutral fact of what happened in the world. Now, your thought may be, and because this may have been my thought years ago, I'm bad at math, or I'm dumb, or this isn't for me, or this is impossible, or whatever that thought might be. But again, is very different from the neutral circumstance of, hey, I took a timed section, say on the quantitative portion, and I got 10 questions wrong. And then the sentence that runs in our mind, as an example, might be, I'm bad at math. All right, well, if that sentence is running in our mind that we choose to believe, we might feel we have a physical sensation or emotion a certain way. In this case, it might be shame, it might be fear, it might be anxiety, depending on what that sentence in your mind is. Now, on the basis of that single line running in our mind, we will take a certain set of actions. Again, speaking from personal experience, struggling with tests on my own without the best resources, is we could take actions like numbing. So that might be ordering Krispy Kreme. Take actions like scrolling on social media. Take actions like procrastination or avoidance. Take actions like complaining, like fighting with our partners, or whatever it might be. And the result that we're going to create with that single thought, that sentence in our mind, I'm bad at math, is going to be, we're going to create the experience. We're going to create a bad experience in the math section or in the quant section and in our lives. So it's incredible that something so simple as a sentence in our mind that we think is objectively true. I'm bad at math. Well, hold on. Let's boil it down to what the objective neutral circumstance was. You got 10 questions wrong on a timed test for a test that you haven't prepared for. You haven't yet reviewed the 25 basic rules of exponents and done 100 practice questions, simple drills, applying those basic rules before diving into the complex quantitative comparison questions. Alternatively, if we go into an intentional frame of this, and we choose to have a different thought with the same circumstance, I got 10 questions wrong. Let's say we choose to think, I figured out complex stuff before. Or whatever it might be. Again, just a sentence in your mind, a particular thought or belief, and in whatever domain or experience that might be. Now, we're going to see We're not going to walk through it all today, but we'll see exactly how this leads to a unique and distinctive feeling, sets of actions, and results, even though we have the same identical circumstance. And this is just going to inform our approach, because oftentimes what we see on the GRE, given that it's a reasoning test, and we're using, again, elementary or secondary or high school level mathematics, that we can get frustrated and we can get stonewalled because we're like, hey, we're just dealing with exponents. But the questions are presented in a tricky way because it's a reasoning test that are integrating 6 or 7 or 12 different exponent rules. Just as in the verbal reasoning section, which we'll tackle head on next week in our webinar, we'll see the same principles apply in formal logic, in logical reasoning. So the language, the logic, the syntax, in this case of mathematics versus of the English language. So just one example of how the thoughts we choose can really govern our behaviors in approaching the tests. All right, so we're wrapping up here. We're here on time and more than happy and thrilled to stay on to answer your questions and speak with you. So as a couple of next steps, you can take a free practice test online, download the GREMax app, and sign up for a free 20-minute consult with a GREMax team member. More than happy to stick on, as I said, this evening. Now, in terms of the tutoring packages that we have, lots of exciting testimonies, but in light of time, we're going to say thank you, bid you a wonderful evening, and more than happy to stick around for any questions, thoughts, reflections whatsoever.